Now we're going to talk about the central processing unit, or CPUs, or our processors. So when we talk about our processors, there are two types of processors out there right now that are mainstream. We have what's called the x86, and we have the x64. And when you hear x86, it's a little confusing because it's actually a 32-bit processor. The reason it's called an x86 is it takes its name from all the processors that led up to it. When Intel first created these processors, they were the 8088 microprocessor, then it was the 8186, then it was the 8286, 8386, 8486, and when they came out with Pentiums, it was the 8586. There was the common thing, the 86 at the end, right? These were all 8-bit and then 16-bit, then 32-bit processors. So when we talk about backwards compatibility, we talk about x86 being 32-bit and below, or 32-bit processors. The newer processors are what called x64, which stands for 64-bit. That one's really easy to see because 64 equals 64, right? You do need to memorize anytime you see x86, it means 32-bit. x64 means 64-bit. AMD and Intel both make x86 and x64 processors. Most processors on the market you're going to deal with today are x64, the 64-bit. With the exception of if you're dealing with any of those little netbooks, those little small laptops, they usually have stripped down processors. They're using 32-bit processors or x86 processors. The reason why is by using that, they can actually have less requirements to run Windows. They're cheaper to make, they're cheaper to operate, and they use less battery life. Less processing power, uses less battery. That way you can have a little laptop that can last you all day battery life. x64 has a lot of benefits to it. It can allow for larger file sizes, a lot more memory, and more complex programs. If you're using a 32-bit system, the maximum you can use is 4 gigabytes of RAM. Okay? If you're using an x64, 64-bit processor, you can use terabytes of RAM. So lots and lots of RAM, which is great for people who like to do virtualization, for people who love to do gaming. Memory is good for that, right? Differences, right? There's different socket types. How does this thing actually plug into the motherboard? That's the socket type we're talking about. Multi-core designs, we'll talk about those in a little bit. Do I have one processor and one core, or do I have one processor with 2 cores, like a dual-core processor? My laptop is a dual-core processor. My computer home is a quad-core processor. It has 4 cores in one chip, which means it's basically doing the work of four machines in one chip. If you have a server, a lot of them have 8-core processors called octo-cores. And so depending on how beefy your processor is, will have more cores, gives you more ability to do more work. And then cache sizes, we'll talk about those as well, but essentially cache is memory inside the chip itself. Okay? Intel and AMD are pretty much fully compatible in terms of Windows. If you're using something like Linux though, you need to have the right software for the right CPU. So if you're going to download a version of Linux and install it, you need to know if you're using x86 or x64 and are you using an Intel chipset or an AMD chipset. Okay. And based on that, you'll download a different piece of software that'll be compiled for that. Windows is compiled to support both equally, it doesn't matter. Okay. So Intel processors. Anytime you see LGA, which is land grid array, we're talking Intel. Okay. It uses this spring-loaded LANs and a hinged clamp mechanism to hold the processor down. You can see it here in the top, right? I'd put the processor in where all those little pins are. I'd flap that down and it would lock in place. The heat sink will snap into the mounting holes at the 4 corners of the processing socket, as shown in this picture on the bottom. You can see the 4 holes that it will bolt into. So when you're talking on this exam, they may ask you a question like, is this particular processor an Intel or an AMD? They may say, the 1366, is that Intel or AMD processor? Or the 775 or the 940, right? How do you know which one's which? Well, one way is you can memorize this whole chart. The other way is my simple method, which works great for this exam, for either the 801 or the either the 801, 802 or the 901, 902. It works the same. If you see a double digit, if you notice here, LGA 775, there's 2 sevens. That means it's Intel. This one, 1366, 66, 2 digits, it's Intel. This one, 1156, 11, makes it Intel, right? 11. Same thing here, 1155, 11, it's Intel. Okay? That doesn't hold true in all of the world, in every processor you're ever going to deal with. But it does for all the ones on the A+ exam in both the Series 8 and Series 9 exams. So it's a trick. Okay? You don't have to memorize it. You can just go, oh, double digits Intel. There you go, right? But But again, if you look through this chart, you'll see that the 775, we have the old Pentium 4s, Pentium Ds, the Celerons. The dual means it was a dual core. The quad means it was a 4-core. And then we got the i7s, i3s, i5s, i7s, and again, each different series as they go through, based on them. Again, all of these are older. The Sandy Bridge is actually what my laptop is. It's a 2011 model. Okay. We're in 2016. It's 5 years old, right? So memorizing the particular number to the particular model, not really that important for you, right? Because you're not going to go out and buy the i7 9XX series processor right now. It's just not worth it because it's a 5-year-old processor, right? But knowing that these are Intel versus AMD is important. So for Intel, or for AMD, excuse me, they don't use LGA, they don't use LANs, they use pins. So they use the pin grid array. And essentially there's pins on the back of the CPU that connect the processor with what's called a zero insertion force, or ZIF mechanism. Okay. The heatsink will then clamp on to the mounting welds on the two sides of it. And you can see here I have a picture of putting the processor in, or in this case taking the processor out. You take this little spring-loaded thing out, it opens up, you then pull the processor out. With the Intel one, we had 4 mounting bolts. On this AMD one, we have 2 clip mechanisms on the side, and you just unclip those. All AMD sockets are going to use the pin grid array with the exception of the F-type socket. Excuse me. So here's a list of AMD ones. The trick with AMD is there's not any double digits. There's one that has a number, it's 940. Everything else is a letter. AM2, AM2 plus, AM3, AM3 plus, FM1, etc., 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 right? If you're a gamer, gamers love AMD chips, okay? Reason why? They can be overclocked, meaning they may advertise it as a 2.6 gigahertz processor, but you may be able to run it at 2.8 or 3.0 gigahertz. Intel doesn't overclock as easily, so a lot of gamers really like AMD stuff. Businesses, on the other hand, tend to prefer Intel chipsets. If you look at Macintosh, they like reliable stuff. And so they have been using Intel since 2005 exclusively. Before that, they're using Motorola. So all their processors are all Intel based. If you're a Windows person, you can use Intel or AMD. Again, it's your choice, based on what you want to build out. But again, AMD does give you a lot of ability to do overclocking. So some CPU technologies. We have HT technology, which is hyper-threading. And we have multi-core. So hyper-threading was originally developed by Intel back with their Pentium series. What it does is it executes 2 threads within a single processor core. It basically has one physical processor, but it emulates 2 CPUs. And this allows faster execution of programs. I'll make this really easy for a beta to understand, okay? There's one of me, right? And there's 2 of you guys. You both have a question for me. So I can either handle one person, I'll handle Nick first and tell Joseph to wait. Or I can handle Joseph and tell Nicholas to wait, right? Or if I want to do this hyper-threading, what I really am doing is I go, okay, I'll give half a second to Nicholas and half a second to Joseph. And I'm working on both you guys simultaneously or fast enough between the two that you don't realize I'm only helping one of you, even though I'm helping both of you. Does that make sense? You're doing kind of 2 things at once, but really, really fast between the 2. That's the idea of hyper-threading. But the limitation is there's still only one of me. I'm only one person, right? If we really wanted to help out the class, and we had a lot of people in class that say, well, one instructor can't do it all. So let's have 2 people. I'll handle the left side of the room. Somebody else will handle the right side of the room. When we do that, we're doing multi-core, right? There's 2 processors at that point dealing with the stuff. What we are in the old days, what servers would do is they actually had 2 physical processor chips, and they had special motherboards and special operating systems that could handle that. Nowadays, what we do is multi-core. We have 1 physical chip. So the software doesn't even understand that there's more than 1 processor. It just thinks there's 1 processor. But inside the chip, there's multiple processors. So my laptop happens to be an i5 processor that it's a dual-core design. It has 1 chip that acts as if it's 2 processors. So it has 2 physical processors inside the 1 chip. And so what it can do is it can actually operate much, much faster and do things in 2 distinct things. And in addition to that, it has hyper-threading. So each of those 2 processors pretends it's 2 processors. So my computer thinks it has 4 processors, even though there's only 2. Okay. And what you can see here on the board, right? If I have 2 dual processors, I have a motherboard here, and I have 2 physical chips that has its own processor and its own cache. If I'm doing dual core, I have 1 processor that shares a cache and has two processors inside the one processor, one chip, right? Hyper-threading, we have one processor that thinks it's two chips. So what you'll see most often nowadays, especially in Intel designs, is a multi-core processor that incorporates hyper-threading as well, like mine does. It has two processors, but each of these processor cores thinks that it's two in addition, so it really pretends it's four, even though there's only two. If that makes sense. Kind of weird, but it works really well. It gives you a lot more capability. It doesn't have additional physical processors, so it's cheaper to make, but it still gives you good performance. Multi-core, in most consumer grade stuff, it's dual core or quad core, which is 2-core or 4-core. If you go to server grade stuff, you'll get into hexa or octa-core, which is 6 or 8. Some servers actually go as high as 16-core as well. If you're a big gamer, most of the gamers are usually in the quad or the hexa core range. Octa if they can afford it, because octa is really, really nice, but they're really expensive. Cache. So what cache is it is memory inside the processor. So we talk about the fact that these processors are operating at 2, 3, and 4 gigahertz of speed, right? Well, when we get to memory, you're going to see that the memory doesn't operate that fast. So what happens is there's a bottleneck as to try and get information to the processor. So what we ended up doing, I say we, like I had something to do with it. So yeah, anyway, so you have the processor core. They have this data cache level 1, which is very small, but very fast. Then they have a bigger cache level 2 that is bigger, but not quite as fast. And then you have the system RAM, which actually has to go out the motherboard to get to it, which is even slower, but can be really big. And what we're talking about here is, like, for instance, the RAM in my particular machine is 16 gigabytes of RAM. Okay. Pretty big number. If I go to the level 1 cache, we're talking about like 8 megabytes of RAM, right? Which is like 1/100th of the size, like much, much smaller. If we go into the level 1 cache, it may be 128 kilobytes of RAM, like 1,000th of the size of my total memory, right? But again, as I'm bottlenecking, we're trying to get better and better performance. So why this is important, when you're looking for a computer and you're looking at the cache, this is something that most consumers don't look at, right? So it's something that manufacturers can skimp on, right? So if you're looking for something good, like you're trying to build that really good gaming machine, you want ones that have bigger caches. You want bigger caches. The bigger size cache, like 128K, is better than an 8K cache, right? An 8 meg cache for level 2 is better than a 2 meg cache. More memory is better. Some processors on high-end units and gaming units will actually have a level 3 cache as well, which may be like 64 megabytes. It gives you that third layer before it even gets to the system RAM as well. And that's going to be better. What the processor does when it's looking for information is it starts at itself and it starts going out further each time. The further I have to go for information, the longer it takes me, right? So if I can find it in level 1 cache, I've got it right there. It's like on the desk in front of me, I can grab it. If I need to go to level 2 cache, I might need to walk over to Nick's desk and grab it. Takes me a little longer, right? If I go to level 3 cache, I'm going to Sarah's desk. If I need to go to memory, like RAM, I have to go to the hallway. If I need to go to the hard drive, I need to go out to my car in the parking lot. And every time I go further, it takes me longer to get stuff, right? So I want the information as close as possible. So that's what the memory is trying to do. It's constantly trying to preemptively think, what's the processor going to need next to start pushing that information to cache so it's ready for it when it needs it. Bigger the cache, the better the performance. That's really what it comes down to. The bus. So we talked about the bus a little bit when we talked about the city bus of the motherboard. Your bus is all those electrical connections on the motherboard. They are the communication system that transfers your data between the components and the central processing unit. The bus speed is the speed at how fast it operates. And unlike speeds in Maryland, you actually have to follow the speed limit. Okay, you can't go faster or things won't talk right. Can't go slower or things won't talk right. So if it says 55 miles an hour, you're going to go 55 miles an hour, right? In this case, we're talking about how fast the bus is operating. We're going to talk about something like 233 megahertz, 533 megahertz, something like that. In some motherboards, the speed can be adjusted in the BIOS. If you're going to do overclocking, you're going to have to adjust this type of stuff, right? Your speed is measured in clock cycles, usually in megahertz when you're talking bus speed. When you're talking processors, you're talking gigahertz. The input-output ports and expansion slots, speeds are determined by the capabilities and designs of the devices. So if you're dealing with FireWire or parallel or serial or SATA, all these things have different bus speeds. For instance, a serial port operates at like 115K kilobits per second, right? Whereas FireWire, we can do something like 800 megabytes per second. Much, much faster, right? If I go to SATA, I can go up to 6 gigabytes per second. So different things have different speed interfaces, which makes them faster or slower, right? And some can be configured to a maximum value like a serial port or a minimum value. Serial ports can actually range from 2400 baud or 300 bits per second, 2400 bits per second, all the way up to 115 kilobits per second, or 115,000 bits per second, right? And so it just depends on what you need for the device to talk with. And that brings us to our 32 versus 64-bit discussion. So we mentioned this before with the x86 and the x64, right? 32-bit software can only access less than 4 gigabytes of RAM. If you're using Windows, it has a hard limit of 3.25 gigabytes of memory when you're using 32-bit operating system or 32-bit processor. So here's one of the fun things that you'll see sometimes. A customer will call up and say, hey, I want more memory. Great. You bring out 8 gigs of memory. Their motherboard supports it. You slap in the 8 gigabyte stick. You turn on the computer and it boots up and it only recognizes 3.25 gigabytes of memory. Uh-oh, what happened? Well, you check their operating system, you find out they're running Windows 7 Starter Edition, which is only 32-bit operating system. So now you gotta upgrade their operating system too to support the memory you just put in. So this is one of those hard limits you gotta see. You gotta remember, you will see questions on this where they'll try to trick you on the exam based on that. Okay? So if you're using a 32-bit operating system, even if the processor may be a 64-bit, if the software itself is not 64-bit also, you're not gonna be able to access that extra memory. Athlon 64 was the first 64-bit processor. Because of that, the software wasn't ready for it yet. They made sure that it was backwards compatible, so it can still run all the 32-bit stuff, right? It still runs all the x86 stuff. If you have x64, you can have more than 4 gigabytes RAM. You can actually go up to terabytes of RAM. You do need that 64-bit operating system though, and you can run either 64 or 32-bit programs in a 64-bit processor. If you're running a 32-bit, you can only run 32-bit. That makes sense, right? Okay. Overclocking. Not something you want to do in a business environment, but if you're a gamer, they do this all the time. So it's the process of taking your processor and running it at speeds faster than normal. This will either be done as what's called a multiplier or just by the speed factor. In this case, in the upper right corner, you could see they are multiplying it by 16.5 is their user defined, so they're overclocking this machine by a little bit. And so if you want to figure out how fast this is actually going, you take 16.5 times 148 megahertz, and that would tell you how fast they're running this system. I don't have the math right here in my head to do it, but something about 2 gigahertz is what they're running it. Something like that. Our systems here to be having a class B can actually overclock them as well. The thing you have to worry about when you do overclocking is if you clock the processor higher, it's going to be doing more of those electronic flips, right? It's more cycles per second, which generates more heat. More heat needs to be cooled. If you don't have a proper system and you overclock it, you can burn out the processor faster. It leads to system instability as well. It crashes more often. Those blue screens of death in the wonderful Windows days, right? You may get more of those if you're doing overclocking. Components will run hotter, can lead to damage, and your life cycle of them will not last as long. That computer that may have lasted 5 years may now only last 3 years, right? It also requires more power and more voltage. If this is a laptop, you're going to burn through your battery quicker, right? And it needs more cooling, like we said. Most users don't want to do this. This is really something that gamers love to do in non-production systems. Non-production meaning non-business environment, right? It's not something you're relying on for every day. If this is your gaming machine, it's also the thing you're using to go through college with. You may not want to use that, right? Because you start overclock it, now it crashes, and now you can't get your term paper done, right? Or if it's just your game machine, go for it. It's okay. There are entire bulletin boards and websites dedicated to overclocking. There's an entire community of these guys. They love to overclock their stuff. And they get these huge cooling fans like this, or they'll use liquid cooled. And we'll talk about cooling in another lecture specifically, to make sure you guys understand those different things. And as you can see here on the bottom, this is what happens if you don't cool your processor enough. It gets fried. And that's a very expensive mistake. So, integrated graphics processing units. So, some CPUs will actually have an integrated graphics processing inside of it as well. So for instance, my chip in my laptop is this one on the upper left. It's a Core i5 processor. And you can see it has two chips. It has the bigger chip, which is the processor, and has the second chip, which is the graphics, to run all the graphic systems on here. Very common in laptops, very common in low-end machines for desktops. Most other machines are going to end up having what's called a discrete graphics unit or dedicated card. As you can see here in the bottom, this is a pretty beefy graphics card, and it would be a PCIe X16. As you can see the length of this bottom piece, right? And it gives you the ability to run dual monitors plus an extra HDMI for the TV. It's got its own cooling fan on it because it's going to create a lot of heat. Integrated graphics is good if you're doing non-3D stuff. So if you want to just web surf and do office stuff, do some video playback, some low-end games, you're pretty good with that. If you want to do high-end games, first-person shooters and all that kind of cool stuff, you're going to want a discrete graphics processing unit. If you're doing video and graphics production or computer-aided design, you also want to have that discrete GPU, graphics processing unit. CPU cooling. So with CPU cooling, you have your passive heatsink. What a passive heatsink is it's kind of like a radiator for your car. Well, I think of it that way. Basically, it's a finned metal device that gets the heat away from the processor. It's going to pull that heat up and let air go through it to cool it off. And then what we'll do is we'll put an active sink on top, which is what you can see here with the middle picture with the fan sitting on top of the heatsink, so that it's pulling the air through there quicker to cool it down. So it's active, it's doing something, right? Passive is just the metal that sits there. We'll also put on thermal paste, which is a phase change material. It's a chemical. We'll take the processor, we'll put the thermal paste on the top of it, put the heatsink on top and the fan on top of that. That's the order we put it in. And that helps transfer the heat from the processor to the radiating fins and then pull that out with the fan. We also have our liquid cooling systems, and what liquid cooling does is usually used in games. I'll show you a picture here in the bottom right. It pumps special liquid solution through the computer to a heat exchanger where the fan cools the liquid before it recirculates it through again. This is used for high-performance systems and overclocked systems. It's one of the most efficient ways to cool a computer system, but it's much more expensive and much more complicated. Do you want to get into this liquid cooling system? Liquid cool systems usually between $100 and $200 minimum. Okay, you're talking about just using a fan and a heat sink like we have up on top. Those are like $30 solutions. Much cheaper to use that. But again, if you're going to do something that has a lot of heat, you're going to be looking for that solution with liquid cooling. And here's an example of a question, right? If you have an AMD processor, which of the following would be AMD processors? What do you guys think? 940 and F, right? Because 1366 makes it an Intel. 1155, the 11 makes it an Intel. 940 is AMD. LGA was all about Intel, and then F was for AMD as well. That's our processors.